What we're going to talk about today is optimization, which is actually something we've already been doing, maybe without using the word, and we'll be doing a lot more of throughout the rest of the course. So, and I don't think there's any admin stuff for me to really say. Assignment to do soon, Friday, I think. Okay, so an optimization problem, that word means typically that we're minimizing or maximizing something. So we're optimizing something. And there's many, many types of optimization problems. An example would be this one on the slide, which is minimize. And now we've already have some stuff that maybe some of you have seen before, but maybe some of you haven't. So this little X underneath the min, if you haven't seen that before, that's telling us which variable are we optimizing with respect to. So in words, you could think about this symbol as fiddle with X however you want until the thing there becomes as small as possible. So X is the variable you get to change around. It's the variable that you're optimizing over. And the interpretation of this is that that thing at the top will return the smallest value. So in this case, the smallest value is going to be it's going to be b. Because we have a parabola, we'll make the squared part 0. That's as small as it can be, and then we're left with b. And so we could say the minimum, you could call it f star, you could call it whatever you want. The minimum of that function is b. But some more words we need for the course. So there's this distinction between minimizer and minimum. The minimizer is the value of x that achieves the minimum. And so in this case, it's x equal to a. But the data type of the minimum and the minimizer, here they're both numbers. They could be different. So as we'll talk about later, x could be a vector. The data type of the minimizer, it's going to be an x. So it'll be a vector. But the minimum is just a value. It's still going to be a number. Ali?
If we're just returning the value, then why does it say return the minimum value x up there?
Because it's wrong.
Okay.
And return the minimum value, not x. Yeah, okay, thanks. Good. So this arg thing, if you haven't seen before, it's saying that block of stuff there will return the minimizer. So we could write x star equals arg min of the function. In this case, x equal to a. Fed.
Maximizer is the arg part.
The maximizer or minimizer is the arg. That's the argument. That's the thing that you put in, which gives you the best possible value, whereas the minimum or maximum is the value itself. Okay. So yes, everything I'm going to say today, I may say minimum, I may say maximum. It doesn't really matter. You could always maximize f or minimize minus f. And now we have tools to talk about it, which is great. So if I want to maximize f, I could minimize minus f. That will give us the same maximizer. The minimizer, maximizer will be the same. The value will be different. There'll be a minus sign, but we can just flip it back when we're done. The function itself also has a name. Probably the most common name is the objective function. So objective function means the thing that we are optimizing. And usually we minimize stuff, especially in this course. And in that case, you might also call it a loss function or a cost function, because it's sort of a measure of badness. And you want to make that badness as small as possible. Okay, this is a bit of a technicality. Maybe it's not that important, but the result of an optimization problem might not always be defined. So if I'm maximizing this quadratic, I can just keep making x bigger and bigger. And so we could say it just goes to infinity, and there is no well-defined maximizer here. We just keep making x bigger towards positive or negative infinity in this case. Okay. Any questions or comments so far? Okay. Good. So I alluded to this already, but in this class, and usually in life, not always, but usually, the function that you're optimizing is a scalar valued function, which means it outputs a number. And that kind of makes sense, because if we're trying to make something as big as possible or as small as possible, that thing should probably be a number. Because it's a bit hard to say, well, this vector is bigger than that vector. Maybe you could, but it's really a score. You can think of it that way. But the input parameters or variables or whatever we want to call them is not necessarily going to be a number. And in fact, in most interesting cases, it's not just a number. So there's two separate ways you can think about this, and I'm equally happy either way. You can think of it as you're minimizing over some vector x. And that's this thing in the middle of the slide here. So for example, it's completely reasonable to say minimize with respect to x the 2 norm squared of x, which is, as we talked about before, the sum of squares of the elements of the vector x. And the minimum there would be 0 again, because we're squaring a bunch of things, and so the smallest we can make them is 0. And so the minimizer would be the 0 vector of however the same size as x. It's also fine to think about it as just I'm minimizing over more than one variable. So minimize with respect to x and y. I just made that thing up. Some function of x and y. It's important to me that you see that those two things are the same in the sense that they're not exactly the same, but we're minimizing with respect to more than one parameter in both cases. And you can think of that as a vector and just give it a single name, x. Or you can think of it as I'm going to explicitly write down x, y, z, etc., etc. But either way, you can have multiple parameters, and now you get to fiddle around with x and y to try to make that thing as small as possible. Often it'll just be more convenient to write the thing as a vector or even a matrix later in the course, just because if we have a million parameters, which we will at some point in the course, you rather write down x than that many letters, not that we have that many letters. Okay. So another distinction I'd like to make is this continuous versus discrete distinction. So I like to think about data types, as we've talked about before. Is x a number? Is it a vector? What size is it? Shape? So a very important distinction between types of optimization problems would be, is x continuous or is x discrete? So continuous is what we were talking about earlier. X is some real number. Make the thing as small as possible. But often x can be discrete. So for example, x could be a binary vector. Each value can only be 0 or 1. Or some other discrete situation, integers, categories, all that kind of stuff. And I just wanted to connect this to algorithms and data structures. You've all taken at least one algorithms and data structures class, and often the word algorithm used in those courses, it's actually referring to solving a discrete optimization problem. So for example, finding the shortest path between two nodes in a graph, you could have an algorithm for that, like Dijkstra's algorithm, but in the broader sense, you are solving a discrete optimization problem. The score being the length of the path, and the variables, there are many ways you could think about it, but for example, you could have a binary variable for each edge in the graph. 1 if it's in your path, 0 if it's not in your path. not all configurations there make sense because you can't have an edge over here and an edge over here, and we'll talk a little bit about that. But it's just discrete optimization, but a specific instance of it. I put down dynamic programming on the slide too, so if you covered that in your algorithms course, that is a particular type of optimization problem, and for that type there exists a super efficient way of solving it called dynamic programming. But at the end of the day, you're doing discrete optimization, just a special case of it. So I thought that's a useful connection to make, but aside from saying that, we won't talk very much about discrete optimization in this course. Almost everything will be continuous. Any questions or comments? Okay, so I've intentionally put a bunch of blank space here to keep the answers out of view for a minute. So I'd like to have a discussion for however long it takes. I just want to hear from all of you. The methods we've talked about in this course so far, what optimization problems have we been solving, even if we haven't been using the word optimization? Ben.
For example, for k means, we've tried to maximize the distance between the centroids or something like that to get the Voronoi cell.
Right. So for k means, in fact, on assignment 2, for those of you who have started working on it, you make this very explicit. You actually code up the objective function for k means, and you stick something into the fit function so that it's printed out, and you actually see that objective function going down. So it's true. With k means, the objective function is the sum of squared distances between points and their own cluster means, and we're actually solving this optimization problem. So what are the variables in k means? What's the x? Don't know your name.
Matthew?
Matthew.
The position of the centroids?
Yeah, so mainly it's the position of the centroids, which is, as we've talked about before, n, d continuous variables. And so there, if we took all those centroids and called them w, it might be convenient to write min and then put a little w under it to just conveniently say those are all of our variables. You could also say that the assigning of points to clusters are also our variables, if you wanted to think about it that way. And then it would be kind of a mixed, continuous, discrete optimization problem in the sense that the cluster centers can be any number. Those are continuous variables, and the assignments are categorical, and so those are discrete variables. And certainly we do see mixed optimization problems as well. How about other than k-means? Ali?
In decision trees, we're trying to minimize training error when we're fitting.
Right. So with decision trees, at least the way we presented them in class, and we're trying to minimize training error when we're fitting. So what are the variables there?
The thresholds.
Okay, the thresholds. Anything else? Ali or anyone? Anna?
Depth of the tree?
Okay, the depth of the tree. Yeah, decision trees are a pretty rough example. We had trouble classifying it as parametric versus non-parametric. We get into the same issue here. Is the depth of the tree a parameter? It's a bit of a mess. Yes, it kind of is, and so are which features you're splitting on and all those things. Decision tree will probably be the least clean example, so why don't we talk about some other ones as well? Ian.
For decision trees?
No, so say something other than decision tree.
For k and n, you're minimizing the distance.
Yeah, for k and n, you're minimizing the distance, and this is a very weird one, because with k and n, you are solving the optimization problem in the predict function. And that is unusual in terms of the stuff we're going to talk about in this course. Many things we're going to talk about in this course, the training or fitting or learning or whatever you want to call it, is the solving of the optimization problem. Find the parameters that make this thing work well on the training data, especially for supervised learning, and then you just predict stuff later. So KNN, it's true, we are solving an optimization problem in KNN. At predict time, for that test point, find me the closest point, and that's also an unusual one. So I'm just trying to think. I think we covered quite a lot. So maybe that's good enough. Let's see what I wrote down. Okay, yeah, so we pretty much covered all of this except naive Bayes. With naive Bayes, we were not really solving optimization problems, except I just told you guys we want to estimate the probability of seeing a particular word given a particular y value, and I said let's just count up how many of those we see and divide by the total, and that seemed like a very reasonable thing to do. And then I had this little note in the corner that said, by the way, this is something called maximum likelihood, which we'll talk about later in the course. So in fact, there is a maximizing happening there as well, but the answer is just very easy, and you could just kind of write down the answer and not really think about the fact that you are optimizing anything. But even with naive Bayes, that connection exists. Connor.
Would DB scan be an example of like a maximization thing, because it's trying to kind of, within limitations, get as many nodes into its cluster as it can, sort of?
Connor asked, would DB scan be an example of you're maximizing something because you're trying to get as many nodes into the cluster? Yeah, I didn't write that one down for a reason, which is that I can't really say there is some function and we're minimizing it or maximizing it. It's certainly not that clear what we're doing. And typically, with these non-parametric methods, it's maybe a bit less clear in general. The whole parametric, when we talked about parametric versus non, the whole parametric means, as I said before, there are some parameters that we're fiddling with to learn the thing. And very often, you're actually solving an optimization problem in order to set those parameters. And again, now it's the curse of putting this lecture a little bit earlier. This will be made extremely concrete in the next couple of lectures as we talk about linear regression. Okay. So another thing to point out is different optimization problems have different domains. So the domain is like the space you get to explore in order to try to minimize the thing. So we talked about x being a real number, or how about x in Rd, so x being some d-dimensional vector would be a more general case of what we've been talking about. But other than that, we didn't impose any constraints on what x could be. But you may have bounds in your particular optimization problem, such as x greater than or equal to 0. So if classic optimization problem would be you're trying to schedule shipments of something from one place to another given roads and routes and something like that, and you can't ship a negative amount of stuff on a truck, so you're going to have these variables saying how much stuff do I put on each truck, and it'll have to be non-negative, something like that. So you could also have, instead of just one of these one-sided constraints, you could have bounds, meaning x is between 0 and 1, and this kind of thing shows up all the time as well in practice. So here's a question for you guys. I've been using less than or equal to here. Not strictly less than and not strictly greater than. And whenever you see bounds or constraints written down in optimization problems, it's always less than or equal to. And I just wanted to point out why that is. So here's a question for you to consider. Minimize x such that x is strictly greater than 0. So what's the solution? What's your name?
Tom.
Tom.
There isn't one?
There isn't one. Yeah, why?
Because you can keep going towards 0 as much as you like. And all.
Right, you can keep going towards 0, closer and closer, and so it doesn't quite make sense. So usually the thing you mean is greater than or equal to when you're imposing these bounds or constraints in an optimization problem. Okay, yeah, this ST, well, I never really figured out if it meant such that or subject to, but either one makes sense. Do this such that you satisfy this. Do this subject to the constraints, blah, whatever. Okay, so this brings us into the next part, which is about constraints. I pulled some of this out of the lecture because it won't show up that many times in this course. But those bounds that we were talking about earlier are just special cases of constraints. But constraints could actually take all kinds of forms. And an example is the one over here. So minimize some quadratic function of x such that sine x is less than 0.5. So in general, you can have some function of x less than or equal to 0. You could always try to write things that way, or most of the time, which is a more complex type of constraint than just saying x greater than or equal to 0. So there's actually some curviness to the search space. And another thing I wanted to say, and again, I know this feels very theoretical, and I knew this would happen, but I just had to get some of this stuff out so that we could do the rest of the course with this common language. So that thing there is an inequality constraint, less than or equal to. There are also equality constraints. So you could have sine x equals 0.5 or sine x less than or equal to 0.5. And all I really want to say about that is they're very, very different things. For example, if I'm searching in this room and I say I have to be less than or equal to the aisle, I still have that whole part of the room over there. But if I say x needs to be equal to where the aisle is, instead of searching in a three-dimensional region, just kind of half the room instead of the whole room, I've now constrained myself to just this plane here along the aisle. And so it's restricting the problem much more heavily than the inequality. Okay, let's look at some of these things. So just a toy example, minimize sine x such that sine x greater than 0.5. The objective function and the constraint function don't have to be the same. They just are in this case. So let's unpack this picture here. First question, what is the data type that we're optimizing? It's a continuous number, x. There is just one of them. It is a one-dimensional optimization problem. It's not a vector or something crazier than that. And in blue, I've plotted the objective function. So, of course, this one's a bit funny because sine is periodic, so we're going to have a bunch of solutions. But we're allowed to make x whatever we want, and we want to make the function as small as possible. And so normally we could make it -1 if we could just pick any value we wanted. But we also have this constraint, sine x greater than 0.5. And so what I've put in the blue shading is the parts of the space that we are allowed to search in. Because anywhere outside of the blue shading, sine x is less than 0.5. And so we get infinitely many solutions to this problem, and I've drawn them as stars. Any questions or comments about this picture? Only 4 people asleep, which isn't that bad given given the subject matter. Okay. Fine, good. So I don't want to say too much about constraints. There's only really one place in the course where we're going to heavily talk about them, which is when we talk about non-negative matrix factorization. Later in the course, the name sort of gives it away. There will be something non-negative. There will be some constraints of the form greater than or equal to 0. But that's a few weeks away. So I'll just leave it at that. Okay. The next thing I want to talk about is this idea of convex functions. We very briefly said the word convex when we talked about k-means. We said that k-means produces convex clusters. So there we were talking about convex sets. Here we're talking about convex functions. They are highly related ideas, but slightly different. So let me show the pictures first. So I posted some notes on convex functions that you can also access through the course webpage, which you'll need for assignment 3. But let me first say why actually we care about this before I get into the details. We care about this because in a lot of machine learning, including a lot of this deep learning hype that's going on right now, optimization becomes the hard part. So you decide what you're going to do, you got your data, and then somehow you have to minimize something. You have to do your learning in machine learning. It's not always just an optimization problem, but it very often is. And that can be very difficult. So I was just showing you a parabola, and you're thinking, oh, there's the minimum. It's obvious, right? But if you have 10 million parameters and some very weird-looking function that is based on some giant training set, imagine yourself wandering around in a 10 million dimensional space. That's what 10 million parameters means, right? It means you're wandering around in a 10 million dimensional space looking for something good, and the function itself is very complicated. So that's a very, very difficult thing to do. And if you don't know anything about the function, it's actually impossible. So if you make no assumptions about the function, maybe there's just a negative delta function sitting there somewhere, meaning an infinitely deep, infinitely small well. You're never going to find it because it's infinitely small. You're not going to land exactly there. But usually there are some things we know about the function or some properties we can prove. A very important one being convexity. And if I can prove this thing I'm minimizing is convex, then there's a lot more hope, even in a million-dimensional space. It's a huge area of research, and a lot of people have thought a lot about how do we solve convex optimization problems. And there are very efficient algorithms that actually get the job done. So the reason why we care about all this stuff is if we can understand some properties of the function we're optimizing, A, we know how hard life is going to be. Is this a crazy function? Is this a relatively mild function? And B, not only do we know how hard it's going to be, but we can select appropriate methods. Just like dynamic programming I said earlier is this really cool thing for this specific type of problem that you can use dynamic programming for. And if you didn't notice you could use dynamic programming, you might use something much less efficient. The same thing here. If you don't have the awareness of types of functions, you say, oh, this is convex, great. Now not only do I know things are better than they would have been, but I can select the right methods that can take advantage of the fact that it's convex and actually solve the problem. And the next couple of classes, when we talk about least squares linear regression, it is a convex problem, and we can show that it is, and then we can mess with it a little bit and say, is it still convex, is it not? I want to make this change for this reason. Did I break convexity? If so, am I prepared to deal with the consequences in terms of optimization? Any thoughts on that? Okay. Okay, so there are a bunch of formal ways to define convex functions. One way I like to think about it is that if I draw a line between any 2 points on the curve, that line will be completely above the curve. So here I can pick any 2 points, here and here, draw a line between them. That line is above the parabola. And here's an example of a non-convex function. So I can take those 2 peaks on the 2 wells on the 2 sides. I can draw a line between them, and it's under the function. So one thing you might be thinking about if you've thought about optimization before is this issue of local minima. So one of the very hardest things in a lot of machine learning, again, including deep learning, is the fact that, again, we're searching. That's what optimization really is. We're searching in this d-dimensional space, and the function f tells us for any point where I am right now, how good is that point. That's what f gives us. So we're searching, looking around, many more dimensions than 3, and we might get somewhere and say, I'm really happy here because if I go anywhere from here, things only get worse. And that's what a local minimum means. You've quite possibly heard of this before. And so we have those local minima there in the middle. And that's one thing that convex functions don't have. So if a function is convex, any minimum that it has is a global minimum. So there is not this issue of, I don't want to be working on a machine learning problem. I have an objective function that looks like this. I probably should have said this earlier, but in these especially supervised learning problems, this function is typically a measure of how well am I fitting the training data, which we talked about with decision trees, even though decision tree is a difficult example. But usually it's a measure of how well does my model, how good a job does it do at predicting my training data? And that's why I want to make the thing small, because it's a measure of error between my predictions and training data. And if I can make the thing small, I have low training error. And we've talked about how training error isn't everything, but it is something. So if I find myself over there and I stop in the middle in the local minimum, then there could have been a way better set of parameters out there that I just missed because I got stuck in a local minimum. So if you hear the idea of being stuck in a local minimum, that's what this is referring to. And one thing convexity gives us is we don't have to worry about this, but I just want to not give the false impression that it's true that convexity means you don't have to worry about this, but not all functions with a single minimum are convex. So I don't want to give that false impression. So this function is not convex. You can pick 2 points on it and draw a line, and it'll be under the function, but it still only has that one minimum. So this function is, in a sense, harder to optimize than the first one that we looked at, the parabola, even though you don't have this worry about local minima. Ian?
Sorry, what was the test you did to determine if it was convex or not?
I took 2 points, and I drew a line between them, and I checked, is it entirely above the curve? And the notes on convexity that I posted have some illustrations to show that. Okay, I'm just gonna, what's your name?
Gareth.
Gareth.
Sorry, why is that more difficult to minimize? You'd think that you'd follow the lines down.
Yeah, why is that more difficult to minimize? So that's basically beyond the scope of the course. Computer Science 406, which is the optimization course, probably talks more about that. By the way, who's in 406? Just curious, right now? Or has taken it? Very few. Interesting. Okay. And again, don't be fooled by all these things looking very easy, because imagine 10,000 dimensional versions of this. Makes things harder. Okay, I'm just going to scroll up. Is there anything I wanted to say? No, I said that. Fine. Going down. I said this. Okay. Okay, so this is not an optimization course, so we won't have entire chunks of the course answering that kind of question that Gareth was asking. But I'll say a couple of things here about it, and then I'll kind of leave you alone mostly for the rest of the course. So we will have a lecture, 2 or 3 lectures from now, on gradient descent, which is one optimization algorithm. But I sometimes get the question, why is this hard? Because I learned that I can find a critical point or a minimum or whatever you want to call it by taking the derivative of the thing and setting it to 0. So it's true. If you can take the derivative of the thing and set it to 0, you've done much of the work that needs to be done. Maybe the derivative is 0 in 100 places. Maybe some are local maxima, minima, whatever, saddle points. You can just check each one, see which one is the best. You're done, fine. But I don't want you to have the misconception that setting the derivative and equating it to 0 is an easy thing to do. Because the derivative, or in more dimensions, the gradient, is itself a function of x. So you have some function of x equals 0, and you're saying, I need to find the x to make that true. That is a hard thing to do in general. I mean, you can take, for those who haven't, Computer Science 302, much of the course is dedicated to solving equations. And we sometimes get this impression in, say, high school or somewhere that, oh, I can just solve equations. I don't know, plug some stuff in, solve. Maybe it's a linear system, and then it's not so bad, do some matrix thing. But in general, for whatever weird equation you come up with, you can't just get the solution. So I just made up some weird looking thing. I never actually looked into it too much, but my point is, if I asked you to find x that made that thing true, that wouldn't be a lot of fun. It also wouldn't be that horrible because it's in one dimension, and so you could even make a grid or do more sophisticated things. But imagine that kind of world in 1,000 variables. There's not just the solution pops out easily. You actually have to do hard work, taking up a large portion of a course in this department to deal with that kind of thing. And it usually involves some kind of iterative method. I start somewhere, I improve it. And indeed, that will be our approach with optimization as well. So there's this parallel between optimizing things and solving equations. And they're not exactly the same problem, but they're quite highly related. Any thoughts on that? Okay. So for those of you who have taken 302, great. And if you haven't, that's also completely fine for this course. Okay, there's a lot of words here. We don't really need to go through them all right now. Yeah, said that. Fine. Moving on. Okay, last thing. I just added this morning because a bunch of students were confused about this last time. There's a few different ways that we use, max and min. And I've put them into 3 categories. I don't know if these are the definitive categories. I just made them up. But roughly, when we write down max or min, sometimes we mean maximizing a function over its domain or minimizing. That's what we were talking about all of today. And the output of that thing is either a number if you're looking for the maximum, or a vector or whatever the data type of x was if you're minimizing. If you're looking for the maximizer or minimizer. And there are functions that do this. Here's one Python function that does this. We'll be getting more into this later in the course. Number 2 is selecting the largest element from a set. So I have some finite set of things. Which one's the biggest? You can use max to mean that. And the output is a number, the biggest thing. And np.max will do that. And the third one, this is the one that really tripped up some students last time in 340, is I could take the maximum of 2 or more functions, and I could write it like that. And the output of that thing is itself a function. So I want to talk about that a little bit. But let's get to the example. So here's case 2. Case 2. X is some collection of numbers. Which one's the biggest? Oh, and by the way, since we learned this stuff today, what's this going to output? 2, right. It's going to output 2 because it is the index of it's the thing that makes it biggest. In this case, all we have to describe that is the index. Okay. So this throws an error. Fine. It means something different in Python. And here's this other case, okay? So here's 2 functions for you, x squared and square root x. If I tell you the max of x squared and square root x, you can't just say, oh, x squared is bigger, obviously. Just like I said, 100 is obviously bigger than 0. It depends on x. Which one is going to be bigger? Sometimes one is bigger, sometimes the other. You can just see them crossing over there, right? So first square root is bigger, then x squared is bigger. The max of x squared and x depends on which x you pick. So you plug in x, you compute the 2 things, see which one's bigger, that's the value you return. And so if I write this in Python with np.maximum, it looks like this. In other words, the max of f of x and g of x is another function of x. And we could also code it up differently. Yeah, this throws an error. We don't need to do that. If this is not helpful, you can ignore it. But if it is helpful, you could use max to do what we were doing with maximum. You could write a new function h that says, give me an x. I'll check f. I'll check g. And now they're just 2 numbers. And then I'll use good old max that just tells me which of 2 numbers is bigger and returns that number. And that'll be the output of h for that x. And if I plot this, I get exactly the same thing. So yeah, okay. Please ask about this if you have questions. I'd like to get this cleared up. Yeah, Ian.
Why would we care about producing the maximum of like 2 functions?
Why would we care about producing the maximum of 2 functions? We care about it because it is a convenient and compact way of expressing piecewise functions. So you could also think of this as, where's the crossing point? 1, I guess. So you could also express this as the piecewise function if x less than 1, square root x, else x squared. But it's much more concise to just write max of x and x squared. It's the same thing. The max of two functions is a piecewise function. In fact, if they cross over many times, it would be much worse, because you'd have to say, in this interval this, in that interval that, in this interval this. But max is just, boom, done. You express it all in one. And this function in particular, we use quite a lot in 340. So maybe just take 1 minute to think in your head, what's that going to look like? The max of 0 and 1 minus x. Or even max of 0 and x, if that's easier for you to think about. Let's do that. Okay, I'm going to run it. Oh, wrong bounds. Ugh, fine. Okay. So if this is what you were thinking, great. If it's not, maybe ponder it later after class. But x is just the line, y equals x. And then we're taking the max of 0 in that. So if the thing is less than 0, we're just making it 0. So again, to speak to Ian's question, we could have expressed this as a piecewise function, but it's often very convenient to express it like this. As you'll see in the notes about convexity, one reason why it's convenient is that the max of two convex functions is also a convex function. And often we want to think, is this thing a convex function? Well, I can express it as the max of this convex function and that. Then we just know it's convex. So that's very convenient. And OK, this isn't really that critical, but I'll just show case number 1 in Python. There are many functions for doing this. It's a whole field, optimization. This is not meant as you should always use this particular scipy function. But I can define a function like x minus 5 squared plus 3. I can give it some random initialization. I can run this scipy minimize. And it gives me the minimum is 3, and the argmin is 5, as we would expect. And I can do the same if x is a vector. So I could say minimize the norm of x minus 5 plus 3. And I get some numerical issues. And if you've taken 302, 303, 406, you'll be familiar with numbers that are not exactly the number you hoped for. But it roughly gets the job done. And here the argmin is a vector because we indicated we were minimizing over vectors. So that is it for today. I promise we'll get back to machine learning next class.